There's something almost poetic about the way space hides its biggest truths in the quietest corners. For years, we've spent so much time worrying about the small things, tiny asteroids skimming past Earth, comets barely wider than a city block, little cosmic visitors that make the news, stir excitement, and disappear into the dark again. But while all eyes were turned toward those familiar, manageable threats, something else was unfolding far beyond the edges of our attention. Something much larger, something older, something that was already on its way. And the strange part is, we only found it because it had been hiding in plain sight. The story begins with a comet you probably heard about, 3IATLAS, the interstellar traveler that captured headlines, the one that made NASA scramble to aim nearly every major telescope at a tiny speck racing through our cosmic neighborhood. Atlas was described as extraordinary, unprecedented, even unsettling. But here's the quiet truth. No one said out loud, Atlas was never the main event. Not even close. Compared to what was coming, Atlas was a snowflake, a pebble, a footnote in a cosmic story about to become far bigger than anyone realized. Because while scientists were watching that interstellar scout zip past us, another object, massive beyond anything previously known, was already gliding inward from the darkness. Its name is Bernardinelli-Bernstein, and if you haven't heard that name before, you will. This isn't a comet in the ordinary sense. This is a mega-comet, a frozen mountain large enough to be mistaken for a dwarf planet. Its nucleus alone stretches 137 kilometers across, roughly the distance from Washington, D.C. to Philadelphia. Imagine a slab of ancient ice the size of a small country, drifting silently through interstellar space for millions of years. And now entering ours, it is more than 10,000 times more massive than almost every comet we've ever studied. And yet, somehow, it went unnoticed for decades. For a moment, imagine the vastness of the region it comes from, the Oort Cloud, a distant frozen halo that forms the true border of our solar system. Out there, sunlight is a rumor, temperatures hover just above absolute zero, and objects, icy remnants from 4.5 billion years ago, sleep for eons in total darkness. Comets in the Oort Cloud are supposed to be invisible, dormant, silent. They are not supposed to wake up until they drift close to the warmth of the sun. But Bernardinelli-Bernstein broke that rule. It began waking up long before it should have, and that was the moment everything changed. When astronomers first spotted it in archival images from the Dark Energy Survey, it was already far inside our solar system, around 29 astronomical units from the Sun, near the orbit of Neptune. But after digging deeper, they found earlier images, older traces, older hints. The comet had been moving toward us for years, captured unknowingly in photographs stretching out to 34 astronomical units. It was there the whole time, but something about it didn't behave the way comets usually do. Comets are supposed to remain quiet and frozen until they get close to the Sun, closer than Jupiter, closer even than the frost line where water ice can finally begin to sublimate. Only then do they develop activity. Only then do they sprout tails and comas and the glowing veils that make them beautiful to look at. But Bernardinelli-Bernstein started changing long before that point, far beyond the distance where sunlight should matter, and by 2025, the quiet mystery turned into something astonishing. That was the year ALMA, the Atacama Large Millimeter Array, turned its array of 66 high-precision radio telescopes toward the icy giant. ALMA specializes in detecting the faintest molecular signatures from the coldest corners of the cosmos. And what it found shocked even the calmest astronomers. At 16, 6 astronomical units, more than halfway to Neptune, where sunlight is little more than a thread, ALMA detected carbon monoxide jets erupting from the nucleus. This was the first time in scientific history that such activity had ever been securely observed at such a vast distance. Carbon monoxide shouldn't sublimate this far out. Nothing should be moving, nothing should be changing, nothing should be waking up. But Bernardinelli-Bernstein was. The implications were enormous. Either the comet contains unusually rich supervolatiles, materials like CO, CO2, nitrogen or methane that evaporate even in extreme cold, or something else entirely is happening beneath its frozen crust, something ancient, something we don't fully understand. Suddenly the story was no longer just about a big comet. It was about a giant that shouldn't be awake, yet is. A giant that challenges our entire model of how Oort Cloud objects behave. A giant that forces us to rethink what lies beyond the edge of the solar system. And that raised the question no one wanted to say out loud. If we found this one, how many more are out there? Is Bernardinelli-Bernstein a cosmic accident, a lucky discovery at the perfect moment? Or is it the first of many, a herald of a deeper hidden population we've never been able to detect? Because if something disturbed this one, what else might be following behind it? You can almost feel the quiet wonder in the scientific community, a mixture of awe, curiosity, and a hint of unease. Not fear, just the understanding that the universe is bigger, older, and more dynamic than we once thought. In the soft darkness of space, where billions of icy bodies drift silently for ages, something stirred, something massive, something ancient. And now, it is coming toward the inner solar system, not as a threat, but as a messenger, a reminder that the edges of our cosmic home are not asleep. They are waking up, and we are just beginning to see the first signs of it. If you want to understand Bernardinelli-Bernstein, you have to travel far beyond anything we usually imagine when we think of the solar system. Past Neptune, past the Kuiper Belt, past the scattered disk, where icy worlds drift in slow, chaotic orbits. Beyond all of that, so far beyond that, sunlight becomes little more than a memory, lies the frozen frontier known as the Oort Cloud. It's not a place you can see, not a structure captured in any telescope. It is a theoretical sphere, an ancient shell of icy remnants stretching tens of thousands of astronomical units in every direction. A sphere so vast that if Earth were the size of a pebble, the Oort Cloud would be the size of a mountain. Most people think the solar system ends around Neptune, but the true border, the real edge, is so far away that it might take a spacecraft tens of thousands of years to reach it. In this unimaginable darkness, objects sleep, billions of them, frozen since the dawn of the planets. And it is from this silent reservoir that Bernardinelli-Bernstein emerged. The objects in the Oort Cloud are time capsules, leftovers from the birth of the solar system. Some are fragments of the same icy material that once rained onto early Earth, delivering the water in our oceans and perhaps the raw ingredients of life itself. Others are older still, forming near the young sun before being scattered outward in violent gravitational encounters with Jupiter, Saturn, and the other giant planets. For billions of years, these fragments drifted outward, settling into the deep freeze, so far from the sun that time seems to stop. Their orbits stretch across tens of millions of years. Their motion is almost imperceptible. They are the fossils of our cosmic past. And then, occasionally, very occasionally, something nudges one of them inward. It could be the gravitational tide of the Milky Way itself, tugging gently on the outer edges of the solar system as the sun makes its slow orbit through the galaxy. It could be a nearby star passing quietly through the interstellar night, shaking loose the most weakly bound objects. Or it could simply be time, the long, patient erosion of orbital stability after billions of years. Whatever the cause, one day, one of those icy relics begins to fall. And in this era, our era, that falling object was Bernardinelli-Bernstein. Its orbit is so long, so stretched, that its farthest point, its aphelion, is estimated near 42,000 astronomical units. A place where the sun is barely brighter than any other star. A place where temperatures hover just a few degrees above absolute zero. For millions of years it drifted there, suspended in a state of near-perfect stillness. We think of comets as small, fragile things, snowballs that erupt in bright jets when they pass near the sun. But out in the Oort Cloud, size doesn't matter. A tiny 1-kilometer comet sits beside a 100-kilometer behemoth, and both are equally silent, equally frozen, That's why no one expected a giant, 137 kilometers wide, on a path inward. Objects this large shouldn't be able to hide. They shouldn't be invisible for so long. But distance hides everything. Even a mountain can disappear if you place it far enough away in the dark. So Bernardinelli-Bernstein slept, unseen, unmeasured, untouched, until its long descent finally brought it close enough for us to glimpse it, accidentally, and only because astronomers were combing through old surveys, built for entirely different purposes. But the most astonishing part is not just that it was found, it's that it was already awake. To understand how strange that is, picture the environment where comets usually begin their transformations. Comets typically turn on around the frost line, the point where ices can sublimate under sunlight. That region lies deep within the inner solar system, somewhere around 5 astronomical units from the sun. There, water ice begins to vaporize, dragging dust into space to form tails and comets. But Bernardinelli-Bernstein began to stir at 16. 6 astronomical units, more than 3 times that distance, a place where sunlight is too weak to melt even the most volatile ices under normal conditions. Its jets of carbon monoxide, detected by ALMA, were the first sign that something unusual was happening inside the nucleus, something ancient, something preserved. Supervolatiles like CO, nitrogen and methane can sublimate at extremely low temperatures. Perhaps Bernardinelli-Bernstein is packed with these fragile ices, the kind that formed in the farthest, coldest regions of the early solar nebula. These materials are so delicate that they might erupt into space, even when the comet is still billions of kilometers from the sun. But another possibility is far more fascinating. Maybe its massive size allowed it to retain an interior so pristine, so untouched, that even now it contains pockets of material not seen anywhere else in the solar system. Imagine a structure layered in frozen sheets, water ice, carbon dioxide ice, rich chemical compounds, and fossilized gases trapped at formation. Beneath those layers, a core warmed only by the faintest radioactive heat, enough to maintain pockets of pressure over billions of years. A structure like that, held together in the deep freeze, could begin to crack as it enters warmer regions, releasing ancient gases that haven't touched sunlight since before Earth even existed. This is why Bernardinelli-Bernstein is not just large, it is unique. It behaves like no comet we've ever studied. It carries secrets older than the planets. It is a piece of the solar system's childhood drifting slowly into view, and it forces us to confront a deeper truth. The Oort Cloud is not a quiet place. It never was. We simply lack the tools to listen. For most of human history, comets were unpredictable visitors, wandering lights that appeared suddenly in the sky and vanished again into darkness. Now, for the first time, we can see farther. We can detect the faintest whispers of activity across billions of kilometers. We can identify objects long before they arrive. And what we're finding is that the outer solar system is not empty. It is full of giants, fragments of the early universe that drift silently through the cold. Bernardinelli-Bernstein is the first we've ever seen of its size, but almost certainly not the last. Its awakening is not just a scientific milestone, it is a message, a quiet reminder that beyond the planets, beyond the warm glow of the sun, lies a vast sphere of ancient worlds, waiting, sleeping, and sometimes beginning to fall inward. We are witnessing one of them now, a traveler from the very edge of our cosmic home, a messenger from the dark, and its journey has only just begun. There are discoveries in astronomy that make scientists pause, not because they are dramatic, but because they are subtle, quiet, and utterly impossible.
The year 2025 brought one of those moments.
By then, Bernardinelli-Bernstein had already captured attention. It was enormous. It was ancient, and it was drifting inward along a path millions of years long. But astronomers expected it to remain frozen, silent, until it reached a much warmer region of the solar system. Objects from the Oort Cloud are supposed to be like that, asleep for most of their journey, unmoving, unchanged. But Bernardinelli-Bernstein had other plans. When the Atacama Large Millimeter Array, ALMA, pointed its 66 synchronized radio dishes toward the distant giant. No one expected anything unusual. ALMA specializes in detecting faint molecular fingerprints from some of the coldest objects in the universe. It can see things invisible to optical telescopes, tiny wisps of gas, fragile molecules drifting through space. The team was hoping for a small signal, a hint, a whisper. What they found was a shout at a distance of 16.6 astronomical units, far beyond Saturn's orbit, where sunlight is as thin as a quiet breath. ALMA detected unmistakable carbon monoxide emission lines, bright, clear, repeated. A comet was outgassing, but not just any comet. A comet 137 kilometers wide, a comet billions of years old, a comet stirring to life in a place where nothing should be active at all. It was the first time in astronomy history that such definitive molecular activity had been observed at such a staggering distance. This wasn't noise. This wasn't a one-time anomaly. It was a pattern, a rhythm, a pulse of gas erupting from deep within the nucleus, jets of carbon monoxide escaping into the dark. Carbon monoxide is one of the most fragile ices in the solar system. It sublimates at temperatures where water ice remains locked solid. But even CO should be sluggish this far out, barely able to escape the surface. Yet here it was, a mega-comet sneezing into space as if awakening from a frozen slumber. The implications were immediate and profound. For one, it meant Bernardinelli-Bernstein must contain an enormous reservoir of supervolatiles. These gases, CO2, nitrogen, methane, are relics of the coldest regions of the early solar nebula. They freeze at temperatures so low that even the frost of deep space can feel warm by comparison. Finding them here now, at this distance, suggests that the interior of B has remained unchanged for 4.5 billion years, a sealed archive of chemical conditions at the birth of the solar system. But the real surprise was the pattern. ALMA saw hints of localized activity, multiple jets, coming from specific regions rather than a smooth, uniform surface. And there were signs that these jets changed between observations. This meant Bernardinelli-Bernstein wasn't just waking up. It was dynamic. Its crust was fractured. Its ices were distributed unevenly. Its internal structure was complex, layered, ancient, and alive with shifting thermal stresses as it moved gradually into warmer regions. Even more intriguing was the detection of faint dust emission, evidence of tiny grains being lifted off the surface by those gas jets. Dust shouldn't be released this far out unless the gas is strong enough to pull it free. And somehow, against expectations, it was... What makes this so extraordinary is that comets normally don't behave like this until they are much closer to the sun. Most of the comets we've studied begin outgassing only when water ice sublimates, inside 5 astronomical units. Before that, they're dark, inert rocks. But Bernardinelli-Bernstein is rewriting that rule. It is showing us that size matters, mass matters, composition matters. A nucleus this large can insulate its interior for billions of years. It can trap volatiles deep within sealed pockets, releasing them only when cracks form or internal pressure builds. Its structure is not simple, but layered, like an ancient archive formed in the coldest part of the solar system. And because of its size, heat penetrates slowly, producing long, gradual waves of activity rather than sudden bursts. Bernardinelli-Bernstein is not a firework. It is a glacier cracking open in slow motion, a process so delicate and ancient that we are only now seeing it unfold, molecule by molecule, across the cold void of space. The 2025 ALMA detection was more than a scientific milestone. It was a revelation, a demonstration that the Oort Cloud contains not just small icy fragments, but massive, volatile-rich bodies that defy expectations. It told astronomers that the giant comets, once only theoretical possibilities, are real, active, and far more complex than imagined. And it forced scientists to confront a deeper, more unsettling question. If Bernardinelli-Bernstein is waking up this far from the sun, what else could be out there? Sleeping giants, quietly waiting for their time to fall inward. This was the moment the narrative changed. Bernardinelli-Bernstein was no longer just a large comet. It became a messenger, a signal that the outer solar system is more dynamic, more populated, and more mysterious than we ever believed. And the closer it comes, the more secrets it reveals. To understand the true scale of Bernardinelli-Bernstein, you have to set aside everything you know about comets, because almost nothing about this object fits the quiet, familiar picture of a comet streaking softly through the inner solar system. This is something different, something on the borderline between a comet, a minor planet, and an ancient frozen world. Start with the numbers. The nucleus of Bernardinelli-Bernstein is 137 kilometers wide. That's not an estimate made from a blurry silhouette. It's a size confirmed through thermal emission, optical data, and modeling. Picture that for a moment. Imagine an ice mountain stretching from Washington, D.C. to Philadelphia. Imagine it drifting through the dark at thousands of kilometers per hour, wrapped in a thin halo of dust and gas, older than the continents on Earth. Where most comets are fragile clusters of loosely packed dust, 5, maybe 10 kilometers across, Bernardinelli-Bernstein is a monolith. A deep core relic, a structure so massive that it holds onto its own form even after billions of years of gravitational nudges. It is more than 10,000 times more massive than the typical comets we see brighten in the night sky. And yet, despite its size, it remains faint, not because it lacks activity, but because the sheer distance between it and the Sun makes even a giant look small. What makes Bernardinelli-Bernstein especially remarkable is not just its physical scale, but the way it moves. Its orbit is a slow, sweeping ellipse, stretching across millions of years, out toward the far reaches of the Oort Cloud and back in again. The aphelion, its farthest point from the Sun, lies around 42,000 astronomical units. That is nearly 700 times farther than Earth, at a place where sunlight is little more than a pale star glowing in the void. And yet, gravity still binds it, barely, but enough to bring it home again after millions of years. From that unimaginable distance, it began its long descent inward, slow at first, barely moving, in a place where motion itself feels like a memory. But as it fell toward the Sun, a speed began to build, not suddenly, not violently, but gradually, like a glacier drifting down a very long slope of gravity. For millions of years, Bernardinelli-Bernstein was a quiet traveler. Then a turn, a shift, a path angled downward into the solar system we know. Today, it is approaching what astronomers call perihelion, the closest point to the Sun on its current orbit. That will happen around January 2031, but close is relative in cosmic terms. Even at its closest, Bernardinelli-Bernstein will remain around 10.95 astronomical units from the Sun, just beyond the orbit of Saturn. It will never come near Earth. It will never cross our planet's path. It will simply glide through the outer regions of the planetary system and vanish again into darkness. And yet, this passage matters, because this is the closest Bernardinelli-Bernstein has been to the Sun in millions of years. Its previous perihelion, based on orbital calculations, was around 3.5 million years ago, and that time it reached only about 18 astronomical units. This time, it is coming in closer. This may be the closest it has ever come in all of recorded gravitational history since the solar system formed, and when it swings past perihelion, this giant will begin its retreat, slowly, patiently, fading into the unlit frontier until it becomes invisible once more. If we don't study it now, we will lose it forever. Not metaphorically, literally, it will disappear into the Oort Cloud for millions of years, long after humanity's civilizations have risen and fallen, long after Earth has transformed into a different world. But what can we actually observe? As Bernardinelli-Bernstein approaches the Sun, activity will increase, not dramatically, not with the fanfare of a bright comet tail, because it will still be too far away for water ice to sublimate. But other materials will awaken. The coma, the cloud of dust and gas around the nucleus, will expand. Carbon monoxide and carbon dioxide jets may intensify. Dust lifted off the surface may form faint structures that scientists can trace. But the comet will never shine in visible light like a classic great comet. Its distance will keep it dim, more a scientific treasure than a spectacle for the naked eye. Ground-based telescopes will study its brightness. ALMA will track its molecular fingerprints. Infrared observatories will pick up thermal emissions and reveal the structure of its coma. Space telescopes may catch its silhouette against the black, and through all these observations, scientists will learn something extraordinary: how a massive comet wakes up, breathes, and evolves. The reason this is so important is simple. We have never before observed a comet this large, this active, this pristine at these distances, and no one knows exactly how it will behave. Will it brighten steadily? Will it undergo sudden outbursts as cracks open in its surface? Will it fragment under thermal stress? Will it reveal layers of material untouched since the early solar system? Even a few unexpected behaviors could change everything we thought we understood about Oort Cloud bodies. Because Bernardinelli-Bernstein is not a typical visitor. It is a survivor, a fossil of the solar system's birth, a wandering glacier that has held its secrets through 4.5 billion years of cosmic solitude. And now, for a brief moment, just a few years in human time, we get to watch it come alive, not with the fireworks of a bright tale, but with the slow, ancient breath of a giant stirring after an eternity in the cold. Every kilometer it travels inward is a chapter in a story we've never been able to read before. Every molecule it releases is a whisper from the dawn of the planets. And every observation we make becomes part of a new map. A map not just of a comet, but of the solar system's forgotten frontier. A map of a place where worlds like Bernardinelli-Bernstein sleep, waiting for the long fall home. When Bernardinelli-Bernstein first revealed itself, astronomers celebrated the discovery. A comet of unprecedented size, a fossil from the outskirts of the solar system, a once-in-a-lifetime opportunity. But once the excitement settled, a quieter, deeper question began to rise. It began as a whisper in conference rooms, a late-night discussion after a seminar, a half-joking comment over coffee. If we found one this big, how many more are there? Because statistically, discoveries like this shouldn't happen. Not easily, not by accident, not by stumbling across old survey data. And yet, that's exactly how Bernardinelli-Bernstein was found. Not in a targeted search, not through some specialized comet-hunting mission, but in the background of a project designed to study galaxies and dark energy. Double B was never the goal. It was a ghost that happened to walk through the frame. If something that massive, something 137 kilometers across, can hide from us until it's already inside the solar system, what does that say about the billions of smaller, darker, colder objects still drifting in the Oort Cloud? To explore the question, imagine the nature of scientific discovery itself. Most of the comets we've known throughout history were atmospheric visitors, bright enough to be seen by the naked eye as they passed near the sun. That means only a tiny subset of comets were ever visible at all, the small ones that came close, heated up fast, and produced dramatic tails. Larger comets, ironically, are often less visible. Their immense mass makes them harder to heat. Their surfaces stay cold longer, they release less dust relative to their size, and if they never approach the inner solar system, they stay invisible forever. So for centuries, our picture of the comet population was biased toward the bright, the small, and the active. It's like assuming the tallest mountains on Earth are small hills, just because the real mountains are hidden behind clouds. Bernardinelli-Bernstein challenges that illusion. It is a mountain that stepped out of the fog, and scientists now wonder, is double B a rare exception, or the first hint of a hidden majority? One hypothesis suggests Bernardinelli-Bernstein is a statistical outlier, perhaps a 1-in-a-million relic, a cosmic accident kicked inward by a lucky alignment of galactic tides and stellar nudges. If so, then we are witnessing something incredibly rare, a giant comet passing through the inner solar system during the brief century when humanity has telescopes capable of observing it. But the alternative hypothesis is far more intriguing and far more unsettling. What if Bernardinelli-Bernstein is not unusual at all? What if the Oort Cloud contains thousands of similar giants, 100 kilometers, 200 kilometers, maybe even 300 kilometers across, silent, cold, and invisible in the darkness? What if the solar system's true mass distribution lies not in the planets we know, but in the uncharted icy vault at the edge of space? This idea isn't science fiction. It's a legitimate research question, one that astronomers are now forced to consider seriously, because every new observation suggests our previous models were incomplete. We know the Oort Cloud likely contains trillions of icy bodies. We know its total mass is uncertain, estimated anywhere from a few Earth masses to dozens. We know the region is largely invisible from Earth, detectable only when one of its residents begins the long fall inward. And we know this. If double B exists, it probably isn't alone. Statistically, single outliers like this are rare only when the underlying population is tiny. But if the population is huge, millions of objects, then giant comets become inevitable. We simply haven't seen them yet. Think of it this way. If you beachcomb on a shoreline and happen to find a giant shell on your first day, chances are good the ocean holds many more. Bernardinelli-Bernstein may be that first giant shell. Another clue comes from how it was discovered. The only reason double B was detected is because astronomers happened to check archival data with updated algorithms, newer, sharper, more sensitive. It wasn't discovered by a telescope pointed at the Oort Cloud. It wasn't found because it was bright. It wasn't found because it was active. It was found because of modern data mining. And that means one thing. If our tools become more powerful, we will likely find more. New surveys like the Vera Rubin Observatory will scan the entire sky repeatedly, building a dynamic map of faint, slow-moving objects. Machine learning systems will sift through immense datasets, picking out anomalies the human eye could never spot. Infrared telescopes will detect cold, distant objects that don't reflect enough light to be seen. For the first time in history, we are gaining the ability to detect the invisible. Perhaps the real question is not, why did we find Bernardinelli-Bernstein? But, how many have we missed?
There is also the possibility of detection bias working in reverse. Small comets become bright when they approach the sun.
Their activity is explosive compared to their size, making them easier to see. But large comets need far more energy to heat their enormous surfaces. They awaken slowly, silently. They glow faintly. So paradoxically, small comets may be easier to find than giant ones. And that means the Oort Cloud's hidden giants could be far more numerous than we ever imagined. One theory proposes that 1 to 5% of the Oort Cloud's total mass may be locked in large dormant bodies. If that's true, then Bernardinelli-Bernstein is not an accident. It's an inevitability, a preview, a messenger, the first chapter of a much larger story. A story in which the Oort Cloud is not a quiet storage zone, but a vast, dynamic reservoir of icy worlds. A place where ancient giants sleep, waiting for the gentle push that will send them inward across the ages. And maybe, just maybe, Bernardinelli-Bernstein is the first giant to step out of the shadows in our time, but not the last. When a comet as large as Bernardinelli-Bernstein begins its long descent toward the sun, we tend to assume the cause must be simple. Gravity, the quiet pull of the solar system, the natural drift of orbits across millions of years. But the truth is more delicate, more mysterious, and far more ancient. Objects in the Oort Cloud do not wake easily. They do not fall inward without reason. For billions of years, Bernardinelli-Bernstein slept in a region where time barely moves, 42,000 astronomical units from the sun, where the faint starlight of our star blends into the glow of the galaxy. For a body drifting so far out, even a whisper of gravitational tug can reshape its path. So what stirred it? What nudged this frozen mountain from its long-held orbit and sent it gliding home? Astronomers consider several possibilities. 1. The galactic tide, the slow breath of the Milky Way. The simplest explanation is also the quietest, the tidal forces of the Milky Way itself. Just as the moon pulls gently on Earth's oceans, the mass of our galaxy pulls on the vast, distant reservoir of Oort Cloud objects. As the Sun orbits the galactic center, once every 230 million years, its position relative to the galactic plane shifts. The gravitational field around it changes subtly. In these shifts, the gentle tug of the galaxy can lift and tilt the orbits of distant icy bodies. Most of the time, these effects are too weak to matter, but across millions of years, small nudges accumulate. Eventually, an object may drift just enough to begin its slow fall inward. Perhaps Bernardinelli-Bernstein is one of these long, patient drifters, the result of a gravitational whisper that began before early humans walked the Earth. 2. A passing star, the hand of a silent visitor. Another possibility is more dramatic. A star may have passed near the solar system, near in cosmic terms, meaning within a few light years. Long ago, such an encounter could have stirred the Oort Cloud, shaking loose dozens or hundreds of objects. Most would drift quietly, some would fall inward, and maybe one of them was Bernardinelli-Bernstein. We know stellar flybys happen. We know Proxima Centauri will come closer in the distant future. We know stars move constantly against the galactic backdrop. And we also know we haven't fully mapped every faint brown dwarf or rogue star that may have passed nearby in the last few million years. A single unknown object could have brushed past the Oort Cloud, leaving no sign except the altered orbits of the icy worlds it disturbed. 3. Orbital chaos, the mathematics of time. Sometimes no external trigger is needed. Over billions of years, the orbits of Oort Cloud objects evolve through chaotic interactions. Tiny variations in initial conditions lead to vast divergences over time. A small gravitational tap from Jupiter millions of years ago, a slight tilt caused by thermal pressure inside the nucleus, or even an ancient collision with another icy fragment could have set Bernardinelli-Bernstein on its current path. In this view, its inward journey is not the result of a singular event, but the culmination of countless tiny influences, a long chain of almost imperceptible nudges adding up across cosmic time. 4. The mystery of its inclination, a hidden clue. But perhaps the most intriguing clue lies in the comet's orbit. Bernardinelli-Bernstein approaches the solar system at an inclination of about 95 degrees, almost perpendicular to the plane of the planets. Most bodies in the solar system orbit in a gentle, shared disk, the remnant of the protoplanetary disk that formed the planets. But Bernardinelli-Bernstein is different. It dives inward almost vertically, like a visitor from a completely separate dimension. This tilt implies something dramatic happened in its past, an event strong enough to wrench it from a more typical orbit and send it drifting into a new orientation. Galactic tides can do this. Stellar flybys can do this. But so could interactions with objects we haven't yet discovered, which leads to the most speculative yet persistent hypothesis. 5. A hidden massive companion, Planet 9, or something else. For years, some astronomers have proposed the existence of a distant, massive planet, sometimes called Planet 9 or Planet X, lurking far beyond Neptune, a planet capable of sculpting the orbits of distant objects, tilting them, clustering them, shaping the outer solar system in ways we haven't fully understood. No such planet has been proven, no direct observation has been made, but if it exists, an object of several Earth masses could easily have perturbed the orbit of a giant comet passing through the far reaches of the solar system. There is no evidence it did, but we cannot rule it out. Not yet. A story without a clear answer. The true cause of Bernardinelli-Bernstein's awakening remains unknown. Perhaps it was a star. Perhaps it was the galaxy. Perhaps it was a hidden world. Perhaps it was simply time. And while speculation is tempting, the beauty of this mystery lies in accepting the unknown. Astronomy is not about having all the answers. It is about learning to listen to the universe even when it speaks in whispers. What we do know is this: Bernardinelli-Bernstein is on its way, slowly, majestically, following a path shaped by forces older than humanity itself. Its awakening is not the product of chaos, but the result of a long, delicate chain of gravitational events woven across millions of years, and as it moves closer to the Sun, we have a chance to watch a cosmic giant reveal the story written in its ice. A story shaped by galaxies, stars, planets, and time. As Bernardinelli-Bernstein continues falling toward the sun, a quieter transformation is happening here on Earth, one that makes its discovery not a coincidence, but a preview of what's coming. For most of human history, comets were things we stumbled upon, a streak of light in the sky, a sudden flare near dawn, a visitor that arrived without warning. We were observers, not seekers. But in the last decade, something changed. Not in the sky, but in our tools. We moved into an era where the universe reveals itself not through what we see, but through what we can analyze. And Bernardinelli-Bernstein is one of the first great discoveries of this new age. It wasn't found through a telescope aimed at a particular patch of sky. It wasn't seen glowing brightly or sending a tail across the horizon. It was discovered because astronomers sifted through old images, terabytes of data from the Dark Energy Survey, looking for patterns the human eye could never catch. A faint pixel here, a slight shift across months, a slow, almost imperceptible motion. This is not traditional astronomy. This is data archaeology, and it tells us something profound. The solar system has always been filled with distant objects. We simply didn't have the means to find them, but now we do. The rise of machine learning and algorithmic sight. Modern discovery doesn't start with the telescope. It begins with software. Algorithms designed to search for the faintest threads of movement across years of sky imaging. These systems can compare millions of stars across dozens of frames. Isolating a point that shifts by a fraction of a pixel, the human eye would miss it. A computer doesn't. Machine learning systems can track long-period comets, identify strange orbits, and flag anomalies in datasets larger than anything a single scientist could ever examine. Bernardinelli-Bernstein wasn't a lucky find. It was the result of this new kind of sight. And that means something important. If we found one giant comet, we will find more. The Vera-Rubin Revolution. And soon, this process will accelerate. The Vera-Rubin Observatory, one of the most ambitious sky mapping projects in history, is preparing to observe the night sky in ways never before possible. When it begins full operations, it will scan the entire visible sky every few nights. Every asteroid, every comet, every slow-moving dot at the edge of the solar system. Captured, tracked, recorded, compared. Over 10 years, its survey will produce an ocean of data, petabytes of images that will allow AI to watch the solar system like a living time-lapse. If another Bernardinelli-Bernstein exists, and almost certainly one does, Rubin will find it. Not by accident, not by luck, but because this time we'll be looking a dusty frontier becoming visible. Until recently, the Oort Cloud was an idea, a theoretical construct that explained long-period comets but was otherwise invisible. Now, for the first time, we are beginning to see its residents before they become bright, active comets. We're seeing distant long-period comets activating too far away, retrograde orbits that don't match classical models, objects with strange inclinations, weak CO emissions in places where no activity should exist. Each discovery is a quiet message from the edge of the solar system, telling us that our models were incomplete. We were studying only the comets that made it to the inner solar system. We were missing the bigger ones, the colder ones, the giants. Bernardinelli-Bernstein opened the door. Our new tools will let us walk through it, a new way of understanding the outer solar system. The more we look, the more we find, and the more we find, the clearer it becomes. The solar system is not static. It is not quiet. It is not empty beyond Neptune. It is a dynamic frontier filled with ancient worlds, some small, some enormous, drifting in slow orbits shaped by stars, galaxies, and time itself. As our instruments sharpen and our algorithms mature, we will continue to uncover the hidden architecture of this frozen frontier. Bernardinelli-Bernstein may feel like a rare event, a once-in-a-lifetime object, but in truth, it may be the first of many, a hint that the Oort Cloud is waking, a reminder that the solar system is far larger than we ever imagined, and a sign that, for the first time in human history, we finally have the tools to listen. If you think of Bernardinelli-Bernstein merely as a comet, you miss the quiet miracle of what it truly is. Because in the vastness of the solar system, there are objects that are not just ice and dust. They are history, preserved perfectly, untouched, unchanged, frozen in time since the solar system was young. Bernardinelli-Bernstein is one of these objects, a messenger from 4.5 billion years ago, carrying within it the chemistry, the temperature gradients, the material composition, and the molecular fingerprints of the era when planets were still forming. Most of what we know about the early solar system comes from indirect clues, meteorites that fell to Earth, observations of distant gas clouds, measurements of planetary atmospheres. But all of these sources have been altered by time, heat, collisions, or chemical evolution. Comets are different. They are preservation chambers, and the larger the comet, the better it preserves. Bernardinelli-Bernstein is the largest pristine comet nucleus ever observed, and that makes it a time capsule unlike any we've ever had access to. A window into the solar system's birth. Inside its massive nucleus are layers of materials deposited in the earliest days of the solar nebula, a swirling disk of gas and dust that surrounded the newborn sun. In that embryonic environment, temperatures varied dramatically from region to region. Specific molecules condensed only under specific conditions. Water ice froze closer in. Carbon dioxide froze farther out. Carbon monoxide, nitrogen, methane, these froze only in the coldest, most distant parts. The ratio of these ices tells an ancient story. How cold the region was where double B formed, how quickly the gas cooled, how much heat penetrated the early nebula, whether organics formed efficiently, and even whether giant planets migrated in their chaotic early years when ALMA detected carbon monoxide jets at 16.6 astronomical units. It wasn't just a measurement, it was a clue that Bernardinelli-Bernstein contains supervolatiles trapped since the solar system's formation, still preserved, still sealed, still capable of revealing chemical signatures from an era older than Earth itself, a laboratory that cannot be built on Earth. What makes double B so extraordinary is that objects like it cannot be replicated, sampled, or reproduced anywhere else in the solar system. We cannot travel back in time to watch the solar nebula form. We cannot rewind the early chaos of planetary migration. We cannot observe the temperature gradients that created the building blocks of life. But we can study the objects that formed during that time. And Bernardinelli-Bernstein is the most pristine, largest, and most ancient such object we have ever encountered with modern instruments. Every molecule it releases, every cojet, every dust particle, every shift in brightness is not just data. It is a message from the universe's past, a message that scientists are now preparing to listen to carefully. Why this moment matters. As double B approaches perihelion in 2031, it will become more active, not dramatically. Its distance means it will never be bright in the sky, but enough for astronomers to study its chemistry in real time. They will measure the ratios of CO, CO2, CH4, N2 and H2O, the dust grain sizes, the structure of its coma, its thermal inertia, and any changes caused by warming sunlight. These measurements will reshape our understanding of how the solar system formed. They may reveal new clues about how water and organics were delivered to Earth. They may show whether double B formed near the giants or much farther out. And because this comet is so large, its activity will be stable, measurable, and sustained, unlike smaller comets whose volatile reserves deplete quickly. It is, in a sense, a slow-motion laboratory drifting through space, a once-in-many-lifetimes opportunity. There is a quiet irony in this story. Bernardinelli-Bernstein is enormous, large enough to rival the smallest moons of the outer planets, and yet it will remain faint and invisible to the unaided eye. Its spectacle is not visual. Its beauty is scientific. For astronomers, this is the closest thing to a cosmic gift, a messenger that appears only once across millions of years, and just happens to arrive during an age when humanity is finally able to study it. When it leaves, after 2031, we will not see it again. Not in our lifetimes, not in our civilization, not in the history of our species. By the time it returns, the Earth will be transformed. The continents will have shifted. The skies will look different. The sun itself may have changed. And yet, for these next few years, we are here, present to watch a frozen world from the dawn of the solar system reveal its secrets, quietly, patiently, one molecule at a time. As scientists continued observing Bernardinelli-Bernstein, an unusual feeling settled over the astronomical community. It wasn't fear. It wasn't excitement. It wasn't even concern. It was curiosity mixed with unease, the subtle recognition that double B might not be a singular discovery, but the first whisper of something larger. A question resurfaced, now louder than before. Is Bernardinelli-Bernstein a cosmic accident, or a representative of something much bigger? To answer that, astronomers explore two primary scenarios, each with enormous implications. Scenario A, double B is a rare outlier, a once-in-a-million visitor. If double B is a statistical fluke, then we are unimaginably lucky to witness it, an object 137 kilometers wide, active at 16.6 astronomical units, carrying pristine volatiles billions of years old, passing by during the short era when humanity has the technology to detect it. If this scenario is true, then double B might be the largest comet we ever observe. No similar giant may appear for thousands or millions of years. Its activity patterns may be unique. Its size and chemistry may not represent the broader population of Oort Cloud bodies. This would make double B a kind of celestial time capsule, arriving just once in the span of human existence, then fading back into the darkness for longer than civilizations can endure. It would be remarkable, but also comforting, because a rare event suggests stability, predictability, quiet. But astronomers are not fully convinced. Why? Because rare events usually require rare causes, and nothing about double B's discovery hints at rarity, only rarity of detection. Scenario B, double B is not alone, a preview of a hidden population. This scenario is far more compelling and far more mysterious. If Bernardinelli-Bernstein is not rare, then its existence implies a hidden population of massive Oort Cloud bodies. Dozens, hundreds, maybe thousands. Most would never come close enough to be seen. Most would remain so cold that no jets would ever ignite. Most would drift invisibly through the galactic night, absorbing starlight so faintly that no telescope on Earth could detect them. But once in a great while, one of them is nudged inward, and for a brief cosmic moment, it becomes visible. If this scenario is true, then double B is simply the first one we've noticed. Not because it's the only one, but because our technology is finally improved enough to see something of its kind. A massive comet waking up at 16 astronomical units is not an anomaly. It is a signpost, a suggestion that the Oort Cloud is far more dynamic than old models predicted. Giant comets may activate in the far outer system. The reservoir of frozen worlds may contain more mass than expected. Gravitational disturbances may send waves of large objects inward from time to time. And if double B is part of a larger population, then the solar system's history becomes more dramatic. The arrival of long-period giants may not be random. It may come in cycles, triggered by galactic tides, passing stars, shifting gravitational harmonics, or other slow, ancient mechanisms. In this view, double B might not be the only visitor. It might be the first, the leading edge of a gradual wave, not a threat, but a revelation. Scientific implications of a hidden population. If many Bernardinelli-Bernstein-sized comets exist, it changes everything we thought we knew about the outer solar system. Mass budget. The Oort Cloud may contain far more mass than estimated. Formation models. Large bodies must have formed efficiently in the early nebula. Planetary migration. The giants, Jupiter, Saturn, Uranus, Neptune, may have scattered more large planetesimals than thought. Long-term dynamics. The solar system may periodically experience surges of inward-bound comets. Planetary defense. Although double B poses no threat, future objects, smaller but faster, could cross Earth's path. But even with all these implications, the tone remains calm, measured, patient, because Oort Cloud giants, even if numerous, operate on timescales so vast that they are almost serene. They drift inward over millions of years. They brighten slowly. They leave quietly. They are not harbingers of danger. They are keepers of secrets, the mystery at the edge. In the end, both scenarios, rare outlier or hidden population, carry a sense of wonder. If double B is unique, we are witnessing a miracle. If double B is common, we are witnessing the beginning of a new chapter in astronomy. Either way, Bernardinelli-Bernstein stands on the threshold between what we know and what lies beyond, a silent emissary from the frozen frontier, reminding us that the solar system is larger, older, and more mysterious than our models ever allowed us to imagine. And the story it brings is only just beginning to unfold. There is something quietly beautiful about watching the universe reveal itself, not in flashes of brilliance, but in slow, deliberate whispers.
Bernardinelli-Bernstein is one of those whispers.
A single immense comet, but also a symbol of something larger, the awakening of the outer solar system. For centuries, humanity believed the solar system ended near Neptune. Beyond that lay only darkness, emptiness, and silence. But now we know better. We know that far past the planets, past the Kuiper belt, past the scattered disk, there exists a vast, unseen realm filled with ancient worlds. Icy relics left over from the birth of everything we know. The Oort Cloud is not a myth. It is a frozen archive, a cosmic library where billions of stories stored in ice. And Bernardinelli-Bernstein is one of the first volumes ever taken off the shelf. Its long fall inward is not a warning. It is an invitation to look deeper, to think bigger, to open our minds to a solar system far more expansive than the one taught in textbooks. Over the past few years, as telescopes sharpened and algorithms matured, we've caught glimpses of this hidden frontier. Faint long-period comets waking up too far from the sun, objects with retrograde or nearly vertical orbits, hints of supervolatiles freezing in the coldest corners of the early nebula, subtle jets that should not exist in deep space, fragments drifting inward at angles that seem impossible. It is as if the edges of our cosmic neighborhood, quiet for so long, are beginning to stir, and Bernardinelli-Bernstein is the clearest sign yet. Its awakening at 16.6 astronomical units broke the rules. Its size shattered expectations. Its chemistry challenged models. Its orbit deepened mysteries. But more than that, its presence reminds us that the universe is not static. It evolves. It breathes. It surprises. Just as continents shift on Earth and stars drift across the Milky Way, the outer solar system is a living place, a vast stage where icy giants move in patterns shaped by galaxies, tides, and time. And for a brief moment in human history, during our era, with our instruments, we are able to watch one of these giants come alive. As Bernardinelli-Bernstein approaches its 2031 perihelion, scientists will track every molecule it releases, every subtle change in brightness, every new jet that erupts from its frozen surface. These observations will become chapters in a story that has waited 4.5 billion years to be told. And when the comet passes its closest point and begins its slow return to the dark, we will be left with something precious, a deeper understanding of how our solar system began, a clearer map of what exists beyond the planets, and a renewed sense of humility in the face of cosmic time. Because once Bernardinelli-Bernstein leaves, we will not see it again. Not in our lifetimes. Not in our civilization. Perhaps not even in the lifespan of our species. It will drift outward for millions of years, too faint to detect, too distant to follow, until it disappears into the background of stars. A frozen traveler returning to the silent frontier. But its legacy remains. It taught us that the Oort Cloud is not empty. It taught us that giant comets can wake far earlier than expected. It taught us that data, not just telescopes, is the new frontier of discovery. And perhaps most importantly, it reminded us that wonder still exists, quietly, patiently, waiting to be found. As you imagine this colossal comet gliding through the dark, its jets whispering into space, its ancient ices releasing molecules older than Earth. Let it be a gentle reminder, we are small, the universe is vast, and yet somehow we are here, awake at the perfect moment, to witness a frozen world from the dawn of time return to the light. The outer solar system is awakening, and the story of Bernardinelli-Bernstein is only the beginning. As Bernardinelli-Bernstein fades back into the darkness, remember that every quiet visitor from the edge of our solar system is a reminder of how vast, ancient, and gentle the universe can be. If tonight's journey brought you a sense of wonder or helped your mind drift into a calmer place, I invite you to stay with us. There are countless more stories waiting in the quiet corners of the cosmos, from sleeping stars to wandering planets, from interstellar clouds to the hidden architecture of the Milky Way. So before you close your eyes, tap subscribe and let fall asleep to science. Be your companion in the nights ahead. Tell us in the comments what part of this cosmic journey brought you the most peace and which mystery you'd like to fall asleep to next. Until then, rest well and let the universe hold you gently.